review. And the last time we went over the projection chapter and the Grabschmidt chapter, but we didn't do a numerical example. And so, okay, at the time I just didn't want to do it. It's simple enough, so we'll just go through it very quickly before we continue onwards. So suppose you had this data set here, right? It's a very simple data set. And by the way, this is linear regression, so it's machine learning, basic machine learning. And recall that the equation of a line then is just y equals c plus dt, right? And then you can just turn this graph here into a system of equations, right? C plus d equals to 1. Okay, I hope you see this is y, and then d times dt is just your time axis, or x-axis. So here t is 1, t is 2, t is 3, and then you see the y values over here. And so you just turn this system of equations then into your matrix of coefficients here, right? And so you have ax equals to b, but then recall then that this does not have a particular solution. There is no linear combination of the columns of this matrix A that is going to give you this right-hand side B. And so B is outside of the column space, right? And remember then that in the projection chapter, let me just like jog your memory very quickly, we had some subspace here, A, we'll call it A, right? Or this is our column space in this case, and remember we described the column space or the n-dimensional case by describing a basis for it, right? But okay, the point in the one-dimensional case was we had some vector b, in this case, which is outside of the column space, right? And so we cannot solve ax equals b. What we can do is project that vector down into the column space, find the error, and solve the best possible, right? So what we're solving then is ax hat equals to p. So, okay, you should remember this if you're following. And what this turned out to be then in the n-dimensional case, because here, right, the column space is a two-dimensional plane, right? And we're looking for two vectors, c and d, so some linear combination of this column space to produce this right-hand side b here. But b is sort of shooting outside of the column space, so what we have to do is project it down into the column space, right? Find best possible. And so we said before that all you have to do is make the matrix symmetric by multiplying both sides by the transpose. So here we just end up with A transpose AX is equal to, right, A transpose times B. And it's really just that simple, to be honest with you. It's nothing too complicated that's going on here, and you can solve this pretty easily, to be honest with you. I don't know, should I guess we can just like look at how you would set this out. So the first thing you do is you can look at A transpose A, right? And A transpose would just be 1, 1, 1, 1, 2, 3, right? So you just got some vectors that were standing up to lie down, okay? And then you put back A, 1, 1, 1, 1, 2, 3. So this is A transpose A, and like you should be able to do this multiplication fairly easily by now if you're this far into the course, so I'm not going to like bother talking about that anymore. And what you end up with is a symmetric matrix, right? And so this is A transpose A. So now we can find a solution, right? So it's fairly straightforward, and then we need to look at, so this is A transpose A. We have to find for A transpose B now. So A transpose B on your right hand side would just be, okay, 1, 1, 1, 1, 2, 3. So it's like fairly simple, right? This is why I just like didn't bother at all, because the video was just, oh god, it was getting like too long, right? And here you're just going to get, I think it's 5 and 11? Yeah? I believe so, it's 5 and 11, yeah. Yeah, well, yeah, you can look at this. Yeah, it's 5 and 11. And so this is A transpose B. And then we can just like put the entire system back together, right? So what we end up with is 3, 6, 6 and 14, yeah. And then you put back your x vector here, because remember it was originally A transpose AX, but we only solved for this portion. We substitute back this in, and we substitute back this in. And we can solve pretty easily. So CD is equal to A transpose B, which is 5 and 11. Alright, and you can solve this with Gaussian elimination. So you can, let's just do that very quickly. So you can, I suppose you can take minus 2 of equation 1 and add it to the second equation. Yeah, that should knock out the 6 and produce like zeros there, right? And so you would get, in that case, 3, 6, 5, right? Well, here I just tack on the right hand side b, and you're gonna get 0, 2, and 1, right? Negative 12, yep, 2, and then right hand side was what's exactly 5 and 11, yep, 1, yep. So negative 10, 11, 1. Okay, and so this makes sense, and then you can obviously do, if you wanted to, this is an upper triangular form, so you can do back substitution, but here I would just prefer to put this into reduced row echelon form, and here's pretty easy, right? You just divide the first row by 3, so you get a 1 here, right? And yeah, you could do that if you wanted to. Yeah, I'm trying to see if this makes like any sense though. For some particular reason, like if you divide this by 3, obviously this is going to become 1, this is going to become 2, and then this is 5 divided by 3, which just does not make sense. So if you wanted to put this like into reduced row echelon form though, you can just eliminate above as well, so it wouldn't be that difficult, to be honest. So how would you go about doing this? So this would become a what? You would need 2 times 3 of this guy, right? So this would be 3 as well, right? So you would end up with, let's see, 3, 0, 2, right? And then you would put a 0 up above here as well, right? That's the entire point. And then what would this guy become? I assume this would be a 2. Yeah, this would become a 2, and this would be a 1. Okay. I was trying to do the entire thing out mentally, but for some reason we're just not able to do that. We've been sick for quite some time, so brain just isn't working. But as long as you understand the idea and you can follow some mechanics, then you're good to go. So yeah, we just put this into upper triangular form, and then we just reduce. So this is reduced row echelon form, but this is not quite complete yet, because we can just divide this first row by 3 and divide this second row by 2, and you would just end up with your identity, which is just 1, 0, 0, 1 here, and this would be 2 over 3, and this guy would be 1 over 2, like this. And so now you can literally just read off your values. So you have C here and you have D here, right? And so really it's just as simple as that, right? So C is 2/3 and D is a half, and so your equation comes out to be y is equal to 2/3 and D is just 1/2 T. And so this is your best fit line for this guy up here, right? Which would, I don't know, some line, right? Some best fit line, because obviously there is no one line that can fit through all 3 of them. Okay, yeah, and so this was like fairly, I hope you are following how we put this into reduced row echelon form. You should know how to do that by now, right? So this you see in Gauss-Jordan, for instance, if you're trying to find the inverse. So you put it into upper triangular form, and then you continue eliminating. You eliminate it below the pivots, but then you also go above the pivots as well. And so in this particular case, we would need -3 of this row, and then add it to the first row, right? So that would be your elementary matrix. Take -3 of this row and add it to this row, and so you got a 0 here, and then -3 plus 5 would leave you with a 2 in this position here, and then we divided by 3 and divided by 2, and we were able to just read off the solutions directly, instead of having to do back substitution, which is sometimes can be a bit of a pain. Okay, so this was the numerical example for the projection chapter, and I think the next thing we're supposed to do is a numerical example for Gram-Schmidt, which I didn't do again because I was just like, okay, it's like so simple, right? Like it's not a big deal once you see the formulas. So I guess, is this really okay? Okay, I said I would do it, so let's just do it, right? So suppose you had 3 vectors like A, but it really isn't difficult. Like by any stretch of the imagination, once you understand the concepts. Well, not capital A in this particular case, it would be common A, but then your first chosen vector is you can just call it capital A, like we've already seen before. So A, B in this case is 1, 1, 0, and C is just 1, 1, 1, right? Okay, and so you just pick a starting vector. You could have picked any of them, but we'll just pick this guy as our starting vector, A, right? And so we're good to go there. How do we find capital B, though? Right, so that's the thing. So we said this was just, and you remember that whole thing, you just project down, right, into the subspace, and then you find A transpose the error equals 0, and then if the error, right, is, so A transpose Y, okay, you've seen this before, right? A transpose, let me just write this up. A transpose Y equals to 0. This means then that that vector, right, is in the left null space, right? So if it's in the left null space, then yes, it's perpendicular to the column space of A. And that's exactly what you're looking for. You're looking for your error vector to be precisely perpendicular to your subspace A that you're projecting down into. And that's the whole point of the proof. So I hope you remember that. So what we got was B is just B, right, minus XA, and X is A transpose B, A transpose A, right? A transpose B, or in this case, A transpose B, A transpose A, and then, okay, so this is like the scaling factor, right? And so, okay, this is like fairly simple. Like I don't want to like go over this multiplication. This is like so basic, right? You can see A transpose A is just like you're normalizing, right? This is the part that's normalizing, right? This is the length squared. You're literally dividing by the length squared, right? X transpose X, and you've seen the proof for this as well. So I don't want to go back into that. So you'll see that you're just dividing by 1 every time, and then you can look at this A transpose. This whole A transpose B situation is also fairly straightforward, and you'll find that B is what, 0, 1, 0. Yep. 0, 1, 0, right? So should I just like write that out? I don't know if it's necessary. Let's just do it, man. But it's so simple, like you should. So this is A transpose, and then you just multiply that by B, which is 1, 1, 0, right? And so you can like carry this multiplication through, and you'll see that you get just 1, 1, 0, right? You can look at this literally as like linear combination of rows if you wanted to, or linear combinations of columns. It doesn't matter, right? Yeah, it's just fairly simple stuff, man. It's not. Oh well, in this particular case, B is, yeah, so 1, 1, 0 minus. So if you look at this as a linear combination of rows, like you can see, okay, give me one of the first row, none of the second row, none of the third row, right? So it's just 1, 0, 0. And you get just 0, 1, and 0, right? So 0, 1, 0. Fairly straightforward. So you got B. And then C was just like, okay, what you do is, C, oh yeah, and this portion I was like not entirely sure about for some reason, but then now that I look at it, it just like makes like complete sense, I guess. So A transpose A, yeah, this is just obvious at this point, and then B transpose C over B transpose B, yeah, multiplied by B. Yeah, at the time I suppose I was not very well. I'm still kind of sick actually, so not 100%, but I guess I couldn't see these vectors for some reason at the time, and then I was like, okay, algebraically it makes sense, but this is this scaling factor x, right? So x times A, so this is down on that, that's the projection in the 8th direction, and then this is the projection onto this subspace. So you have like a basis for the column space here, right, A and B, and you're taking away, right, the portion that's going down onto this basis and the portion that's going down this basis as well. And then what remains then has to be, if you can see this, it's like so nice, right? It has to be perpendicular to A and B. Like all three of these vectors are perpendicular to each other, and that's the whole point of an orthonormal basis. Okay, and so you already know what A is, and you already know what B is, and so you can like just, and you know what C is as well, right? It's right here, and so you can just like carry out this pretty simply. So it's 1, 1, 1, right? C minus, right, this guy times A, which I suppose you haven't exactly seen, but okay. Yeah, I don't want to though. It's like such a hassle. Like, come on, you should be able to like carry out this pretty easily, right? But you'll see that A transpose C, A transpose A times A is just going to give you 1, 1, 0. You can do it in your own time. Sorry, 1, 0, 0. And then you do the same thing here, and you're gonna get 0, 1, 0, and you'll see that the basis for third vector is just 0, 0, 1. And then if you look at the three bases, it's just like 0, 1, 0, 0, 0, 1, and 1, 0, 0. These are the unit vectors, right? So yeah, you can obviously see straight away that they are perpendicular to each other. Okay, so I feel like this is fairly simple, and this is Gram-Schmidt, and the entire point of Gram-Schmidt was, if you have an orthonormal basis, then you can say Q transpose Q equals to I, right? And remember before we were doing A transpose X is equal to A transpose B, and we solved that, right? Well, you don't have to do that anymore, because you can just do Q transpose Q, A transpose AX, sorry, and Q transpose QX is equal to Q transpose B. And what is this? This is the identity, so this is gone. You don't have to do this computation anymore. It's just gone, right? And so you have X straight away as just being Q transpose B. It's so nice, right? It's so nice. And Q transpose, right, is like the inverse of Q, like by definition. So like it's so easy to find. You don't have to like do any kind of crazy computation. You just get some vectors that are standing up to lie down, and you have the inverse, right? It's really good. So yeah, you already have your solution like just sitting here, right? So all you have to do is like Q transpose B. It's so fast, right? It's very good. Okay, so that's Gram-Schmidt. So this is like the super optimized way to do linear regression. All right, and so the next chapter I think was on spectral theorem. I'm not sure. I'll have to check my notes. Let's see. Oh yeah, so this is the start of symmetric matrices and spectral theorem. So this is where it starts to get really nice, to be honest with you. So first of all, the first thing you should know about these real symmetric matrices, I should say. So this is like real symmetric matrices. We'll see complex matrices in a bit. So the eigenvalues are real. So obviously, yeah. Eigenvalues are real, and there's something else. Ah, yes. So the eigenvectors, and this is the whole point. The eigenvectors are orthonormal, right? Or perpendicular, however you want to see that. And there was a proof in the lecture on this first part, and I believe you have to go into the book to get this. I think this is like really nice as well, but you can see it as well, so you don't really have to go into the book. But for the eigenvalues being real, there was an entire proof. I'm not going to go into the proof. It's fairly straightforward, but the end of the proof looks like this, and it's just lambda equals to lambda bar at the end of the proof, and you'll see then that the imaginary component has to be non-existent, right? Because if you had a plus bi, and it's equal to its own conjugate a minus bi, right, then you can only assume then that the imaginary part is non-existent, right, for this to hold, right? Because if the imaginary part was something else, this would be a false statement. So lambda equals lambda bar shows that the eigenvalues are in fact real for real symmetric matrices. So okay, I just wanted to like sort of skip through that part. But okay, we've seen before then this factorization, a equals to s lambda s inverse, and you've seen how to diagonalize a matrix, and now you can use this to compute high powers of a matrix as well, like a to the k equals to lambda to the s lambda to the k s inverse, right? But now that you've seen Gram-Schmidt, right, you can, if you can make an orthonormal basis, right, you can get A equals to Q lambda Q inverse, right? And you know that Q inverse then is just Q transpose, right? Because Q transpose, Q transpose Q is I. And so the inverse of Q is simply Q transpose. So this factorization becomes Q lambda Q transpose. And this is like, again, this is so nice, right? You don't have to compute, you don't have to do like Gauss-Jordan or anything here. You just transpose your matrix and that's it. You have the inverse. All right, so what is this though? So this is like your new factorization, like better. It's almost as good as it gets, right? There's like one more factorization of a matrix that you'll do later on in the course called the singular value decomposition. And this is like really just like the best factorization of a matrix you can get. But this guy here is pretty nice, right? This is really, really good. And so this is actually called the spectral theorem. And okay, let me show you what it is, right? So you should like always try to, if you have something like this, you should try to imagine what it looks like, which is what we did before when we were sort of explaining what diagonalization was. And so imagine this, right? You have some matrix Q, right? This is your eigenvector matrix, but this time you have an orthonormal basis, right? All of these eigenvectors are now orthogonal and normalized, right? They're Q. So you get Q1, Q2, all the way to Qn, right? And these are just like vectors. And then you multiply by this lambda matrix here, which is just lambda 1, lambda 2, lambda 3, lambda n. Like you've seen this before. And on this, we don't have space. It sucks. But okay, but then this multiplies, should I write this? I don't want to write this back. But it multiplies Q transpose, right? So this guy here, I'll just put it over here. So Q transpose, which is just like Q1 to Qn. I'm just getting lazy now. But this time it's like, you know, horizontal because it's transpose. It's no longer vertical, it's horizontal, right? And the way to look at this, again, I guess you can look at it by rows, you can look at it by columns. I'll just look at it by linear combination of columns. So we'll take the first column of this transpose matrix, right? And we'll multiply it by this. So what is that exactly? So that's just saying, for instance, right, for this first guy here, we're saying, okay, one of this times this column, right? So a matrix times a vector is going to give you a vector. You know that. So what is our vector is really what I'm trying to get at here. So Q1 times this matrix here is going to give you what? So we're asking for one linear combination. So it's Q times this first column, right? Q1 times this column, Q2 times this column, Q3 times this column. See what's going on there? So you get lambda 1, Q1, all the way to lambda n, Qn, right? So this is what you get after. So this is like matrix times this first vector here, right? We are not looking at all of the columns. We're just looking at one column, and then it'll generalize to all of the other columns. And so now you have this guy here, right? And so, and then it's multiplying what? This guy, this matrix here now, right? So vector times a matrix is going to give you again a vector. Right? So, but what is this vector exactly? So lambda 1 Q1 times Q1. Can you see like what's that? What is that going to be? Oh no, the cats are having their way in the kitchen. Okay, there's nothing there for them. Hopefully. Hopefully. Okay, but I just don't want to pause this to go deal with that right now. Okay, where were we? So vector times, and remember this is like an entire matrix, right? These are just columns coming down here. And so you have this Q1 vector, right? Or this, so it's going to be lambda 1 Q1 times what? This entire Q1 vector, right? Lambda 2 Q2 times Q2 vector, lambda n Qn times Qn vector, right? Eigenvector. So what you end up with is like lambda 1, okay, and oh, by the way, this is Q1 transpose, Qn transpose. That's my bad. Should have put that in there just to be like super clear what's going on there. So lambda 1, right? Q1 transpose. Right. Okay. There we go. So we've got lambda 1 Q1 transpose all the way to lambda n Qn transpose. What are you going to get when you multiply this by this first guy here? You're going to get Q1, right, Q transpose, what am I saying? I'm just getting so tired, but I just have to get this over with. Okay, so Q transpose, that's what you're going to end up with. And remember, this lambda is just like a scalar quantity that you can move around, right? So I don't know if you're seeing this though, that's the thing. I don't know if you're like seeing this. Like lambda 1, this is a 1 I'm supposed to put here, lambda 1 Q1 transpose, right? This is your vector. And you're multiplying this, right, by this guy, so you're taking Q1 times this, right? I don't know if you can see that. So it's like the Q1 is like outside here on the first iteration, and it's multiplying by this guy, right? So it's Q1 transpose. Can you see that? I don't know. I don't think I can do it, like, help you out any more than that, to be honest. So, but hopefully you can see, like, it's just matrix multiplication doing work for you. So it's Q1 transpose, and then you can put like the lambda out in front like this. This is a scalar, so you can put it at the back, you put it at the front, doesn't matter. Okay. And so now the point is then that once you carry through this now for all of them, so Q2 to Qn, right, you're just going to get all the way down to lambda n Qn transpose. Now here's the kicker. Do you recognize this? This is a projection matrix. Like, can you see why? Maybe I'll just like review you very quickly. Remember, like, we had this A transpose error vector equals 0, and then we said that this was A transpose B minus XA, right, equals to 0, and this was like the error vector, right, B minus P way to lambda n qn transpose, right? So this, let me get a different color, put this in blue now. What is this exactly? So this is just like a combination, right? Symmetric matrices is a combination of mutually perpendicular projection matrices. This is the point, right? So this is what a symmetric matrix really is. A combination, right, these plus signs, a combination of mutually perpendicular, right, symmetric projection matrices. So that's a symmetric matrix. Combination of mutually perpendicular projection matrices. So this is a projection matrix, this is a projection matrix, and this is another projection matrix. And so, yeah, so that's the spectral theorem, and I think there's also another name for this. You'll probably get a better understanding of this, I think, on the very next lecture, I think, is when he touched on the principal axis theorem, right? Okay, let me not jump the gun, but for now, you can, like, see this, like, pretty straightforward. And this is used in, like, some pretty major parts of, like, robotics and computer science in general, or even, like, just scientific work in general. This is heavily used. You'll find this all over the place. So I think this was the main gist of the chapter. There's like a couple more stuff here in my notes, but this is like more so just like really personal stuff. I have like a numerical example here with light. Okay, so that's pretty cool, but I won't get into that. You can like get your own example if you want to, but this is just like the gist of it. So I think from here, the next chapter was on, what was the next chapter on? Complex matrices, right? I think the fast Fourier transform. So the next one was the FFT, fast Fourier transform. So let's see, what do I have on this? Oh yes. I remember this was like, oh god. You really do have to do, and in my case, I was just not content with just knowing what Euler's formula was. I needed to see the proof for Euler's formula, and I wanted to derive it. And then, that's just me, right? But like in general, this is like, I think, one of the easier lectures. It's not too difficult to see, but I'll just kind of like walk you through. So first of all, you need to know what is the Fourier matrix, right? So it just looks like this. So I'm just gonna speed run this. This is just, again, as I said in the last video, something to just sort of jog my own memory back to these things. So, okay, matrix of 1, so this is like F4, I think, was an example of, or F to the n in this particular case. So all the way to n, and then this is like all the way to n as well. And the point is, like, if you're counting, right, from 0 to n, right, and you're taking these powers, you'll get W, W2, all the way to W to the n. And I'm just going to jump the gun and show you what the general form is. So the general form for this is W, so F of n, right, I times j entry is, right, W to the I times j. It's as simple as that, right? And so, like, you can imagine, what would the last entry be? Like, let's just do the last entry here. This is the n minus 1 entry. So this is W to the n minus 1 squared, right? So, like, you should be able to fill in all the other entries as well. Fairly simple stuff. And okay, so then why is this value always 1, right? Because this is in the 0th position, right? And then, can you see? Like, anything raised to the 0th power is just 1, right? So, yeah, so that's why the first row and the first column is just completely filled with 1s. Okay. And so what are we looking for, though? What is W in this particular case? What is W? So W is just defined, right, by, so W is W to the n. Anything that satisfies this is considered W. Okay, W to the n equals to 1, and roots of unity, this is called roots of unity, and I hope you know some complex numbers, because I'm not going to get too deep into this. Okay, but W is equal to e to the I 2 pi over n, 2 pi over n. Now, in this form, you're probably not, you may not be familiar with this, but this is called Euler's formula, so I'm just going to give you like a brief recap of where this comes from, maybe. And so if you had your unit circle here, right, and say we had some vector coming in like this, right? This is, we can call this vector z, right? And so z would be in the form a plus bi. It's a complex number, complex plane. And let's say this is I, right? And this z here is I squared, right? And so we know obviously then that in rectangular form this would just be cosine theta plus I sine theta, right? You should be familiar with this. Hopefully you know a little bit of trigonometry. And you can get any angle in this quadrant, right, by raising I to some power. Can you see then that I to the, so I here is just 90 degrees, or pi over 2, right? But I squared, right, or I raised to the half power, I should say. Square root of I is precisely 45 degrees. Can you see that? Like, if you raised I to the half power, like you took like half of this, you would get exactly here. Can you see that? I hope you can see that. And so in general, like if you took like 1/3 or 1/5, like you would be able to move this vector, rotate this vector, right, simply by raising I to a power, which is like really neat. And yeah, you should understand then that all that you're doing with an imaginary number, when you're multiplying by an imaginary number, like if you started with 1 right here, and you multiplied by I, you would get I, right? And so that's a 90-degree rotation. And then if you took I and you multiplied it by I again, right, you would get -1, right? So it's interesting, right? I squared is equal to -1. Yes, that's, well, like obviously the definition, really, in a case. So it's pretty interesting stuff, yeah. So that's another like 90-degree rotation in a sense. Left multiplying, like a left like rotation. Like if you did the opposite, right, you would get a right rotation. And so obviously you keep going, you get -I, and then -I by I is going to give you back 1. And so you can like play around with this and see for yourself. But okay, the point I was trying to get at really is raising I to some power, right, is really just going to correspond to a rotation, right? But then that's the same thing as like a multiplication, which is also corresponding to a rotation. And then you should know obviously then that division actually is, I'm just getting way ahead of myself here, maybe, but it really does test your foundation, right, in mathematics, to know that the inverse operation, right, is, the division is defined in terms of like inverse operation. There really is no quote-unquote division. There's inverse, right? Like for instance, if we had, yeah, let me just show you like very quickly. If we had x plus a equals to, I don't know, b or something, right? And we wanted to like get rid of this b, or we wanted to get rid of the a, right? We will multiply by a inverse, right? And so you would just get x is equal to b times a inverse. And inverse, then, you should know, is just 1 over this guy, 1 upon the reciprocal. That's the inverse, right? That's the multiplicative inverse. Because if you had a, right, over 1, and you multiplied it by 1 over a, this is how you get 1. And that's the multiplicative identity. And you should know that the identity and the inverse are closely correlated. For groups, there's multiplicative group, there's additive group, particularly since the complex numbers are a field, so there are 11 axioms that you should know how to play around with. Alright, so I definitely really segued there, but point being that I, right, theta, raised to some value k, right, can be written in this form, k times 90, so this is what I came up with, k times 90 degrees, okay, but it's not so difficult to come up with either. You can literally see why this is the case. Okay, and so suppose then, right, so what would theta be in this case? Theta would just be, well, I suppose we should solve for k. We want to know what k is, right? So we don't know what power we're raising to. And so k would just be theta over 90 degrees, right? So that should be fairly straightforward. And so let's take an example, 135 degrees. I feel this is fairly simple to see. So what power do we need to raise I to in order to get 135 degrees, right? Because currently we're stuck in this quadrant, but that's what this k factor is going to help us do. It's going to help us, it's like a stretching factor, so we're going to see how much more we need, right? And so this is just going to be 135 over 90, and then you can just carry out this and you'll see you'll get 3 over 2, just get 2 pi over 2 theta over pi. So fairly simple stuff there. So I, right, this is k, remember this is k. So I raised to the 2 theta over pi, right, is going to take you anywhere on this unit circle. Any angle you want to get in radians, you just plug it in here and you're going to get it. Okay, so that's like fairly simple, but now all you're doing, right, is you're going from this guy, right, you're doing a change of base. So instead of I being your base becomes E, right, and we set up here, where was it, E to the I 2 pi over n, right, E to the I 2 pi over n, and this here, this is your angle, right, so it's usually I theta, right, you're probably familiar with this as being I theta, but this case, in this particular case, for roots of unity, it's 2 pi over n. So yeah, hopefully that's fairly straightforward, and you can get the proof for this many ways. Calculus is probably one of the more elegant ways to see this, but okay, I won't be going into that. We don't want to make this video terribly long, but e to the I theta, again, in rectangular form, is equal to cosine theta plus I sine theta. It's really all just the same thing at the end of the day. And then obviously you can take a numerical example, like if you took pi over 2, right, then okay, you should be able to see what's going on here. Alright, so but what do we mean by this 2 pi over 2 situation, like theta being 2 pi over n in this particular case? Right here we said the angle is 2 pi over n. What do we mean by that? Like, think about that very carefully. Like, it's at 2 pi over, like, it's like 1/n of the full way around. Like, if n equals to 6, right, then 2 pi over 6 is like 1/6 the way round, right? And then if you took w to the 6, you would get 1. And so the easiest way to see this is with like your regular the definition of a complex number. That would be w to the 4th, right? That would be like n equals 4, so it would be 2 pi over 4, so that's 1/4 the way around, right? And if you made 4 complete revolutions, you would end up back at 1, right? I hope you're seeing like what's going on there. So it's pretty nice actually, and so that's how I think we get the definition for the Fourier matrix. Do I have like a numerical example here? Of course I do. Yes. Very diligent with my notes, it seems like, when it comes to linear algebra. So there was an example here with 2 pi over 4. So if we took this primitive, right, as w, so e to the 2 pi, e to the 2 pi I over 4. And so what is this exactly? This is just I pi over 2, right? I pi over 2. E I pi over 2. And so this is cosine. Remember we said before, so this is cosine pi over 2 times I sine pi over 2. Okay. And okay, yeah, obviously cosine pi over 2, cosine of 90 is 0, right? And then like sine pi over 2 is just 1, so it's I times 1, and so obviously you get 1, right? And yes, this makes sense, of course. So you get I, right? 1 times I is I, so you get back I. So. Okay, and so the powers of I are just I squared, I to the 3rd, I to the 4th, right? And so it would be, columns, right, are orthogonal, but they're not exactly orthonormal, right? And so to make these orthonormal, because like you look at this, like the length squared would be 1 over. It's like 4, you divide by, multiply by 1 over 2, divide by half. You should, and like you've seen how to divide by the length squared, I guess is what I'm struggling to say for some reason. And you know how to get the length squared. Oh yeah, there is something pretty important that I think I left out, and it was like how to get the length squared. Yeah, I think I might have missed like a pretty critical point of this lecture. And the point is, right, for symmetric matrices, like, so you've met this class of matrices before as A transpose A equals A, right? But this is not true when you're dealing with complex numbers, right? So when you're dealing with, because like the reason I'm bringing this point up now is because you're probably thinking, okay, how am I going to get the length squared, right? You take X transpose X, right? No, it doesn't work like this for complex numbers. And so the thing you have to do is, like, if you had some number like in a complex plane, like Z1 to Zn, Z2 all the way to Zn, like this, right? Z transpose Z is not going to cut it. You need Z transpose conjugate Z. This is what you're looking for, and this is actually called Z Hermitian, after a French mathematician Hermite, right? So Z Hermitian Z is equal to, this is what you're looking for, right? This is going to give you your length squared. Okay, and so the definition then of a symmetric matrix in the sense of complex numbers is going to change. Do I have an example of that here? I'm not sure, so I'm checking. I must have had an example somewhere. Of course, yes. And so suppose then that Z was just, we just had 1 and I, right, as Z, and then we transposed and then conjugated that, so it'd be 1 and negative I, and then we took this product, right? You can see then that we just get 1 plus 1, which is 2. Length squared is 2, so we're good to go there. But this otherwise would not work had we just taken Z transpose Z by itself, right? So it does not work that way, unfortunately. And so what you do then, for a matrix to be considered symmetric if it's complex, right? The complex matrix, A transpose A does not cut it anymore. What you need is A transpose conjugate A, right, equals this, right? This is what's considered to be symmetric in terms of complex numbers. And we said before that this is called Hermitian. So A Hermitian A equals to A. And why is this though? Like, you need to see. So let's do an example here of a symmetric matrix that's complex, 2 and 5. So 3 plus I and 3 minus I. Right, so this is called a Hermitian matrix, and you can see then that if you transpose this matrix, it would flip the diagonal, so you would have 3 plus I here and 3 minus I here, but A transpose is not equal to A. What you need to do is conjugate this guy, right? And so they return back to their previous values. Can you see that? Like, if once you flip, you put this here and you put this here, and then you conjugate, you get back the original matrix. And so that's why we need A Hermitian A equals A. Okay, and so that's how you get this inner product here, right? So that's how you're able to find your length squared and then, you know, normalize. And so now, right, you have an orthonormal basis. Yes, you can use that word orthonormal now because they're unit vectors and they're perpendicular to each other, and you can double check that as well if you wanted to. And now you have some pretty nice properties. For instance, if you have F4, right, so F4, then obviously if you have an orthonormal basis, then that implies that F4 multiplied by F4 Hermitian would give you the identity, obviously. So like your inverse is like sitting right here, so you're like so nice again. Okay, so let's talk about the fast Fourier transform. What you've actually seen here, this is called the discrete Fourier transform, and you can probably tell the time complexity for this is n squared, right? It's n by n matrix, so you'd assume that if you're doing like a multiplication by a vector or something, it would be n squared operations. But the fast Fourier transform, which is actually just a transform modern scientific computing. Like, there's no way to stress how important this is, and it's like used everywhere, to be honest. But the time complexity for this is n log n, which is like an insane improvement from n squared, right? You're going from quadratic to this, like, whoa, right? That's crazy. And so what's the basis for this? The basis for this is, suppose you had your complex plane here, right? And you had, for instance, w to the 64th, and let's just assume that w to the 64th was like sitting here, right? 1/64th of the way around the complex plane, right? That would be the roots of unity. So w to the 32, though, what would that be, right? You can kind of see that it would be somewhere here, right? 1/32 of the way. Can you see that? So w to the 64 squared is going to give you w to the 32. Like, there's a connection here, and that's the entire point of the fast Fourier transform. So insert page after. So this is called the Cooley-Turkey decomposition, and it's really, really nice. So if you had f64, right, f64, and we said now that we know that somehow w32 is connected to w64, right? And what you can do is you can decompose, right, w64, or f64 rather, you can decompose it like this. You can say f32, 0, 0 here. And then there's something here and there's something here. So over here, there's a permutation matrix. I'll tell you what that permutation matrix is in a second. And then there's like a fix-up matrix here. They call it the butterfly matrix, right? And it's just the identity sitting here, a diagonal matrix, and then negative times that diagonal matrix. So now we need to fill in like these values. So what are the permutation matrices? So this is pretty simple. It's like, it looks something like this. Like, but okay, this is not good enough. Like, you need to know like exactly what the permutation matrix is doing. And so suppose we had like some input vector x, right? Like we had x transpose sitting here. And so we had like x1, x0, so let's say x0, x1, x2, all the way to xn, right? What this permutation matrix is defined to do is to take all of the even indices, right, and put them first, right? So say we started with this x transpose, right, and you had the result, right, of this permutation matrix is going to take this even value and put it here. It's going to take this even value and put it here, right? It's taking all the even values and it's going to line them up right next to each other. So you have even values here, and then all of the odd values are going to come here, right, like this. So you have even and odds. So it's literally split your vector, right, into its, not the even numbers, don't get that confused, the even indices inside of that vector. There's no way to know the numbers are even unless you're using like an ALU or something to like manually do the computation, which is horrible. And so this, right, so far we're at 64 squared, right here. This is what we're at. We're at 64 squared, which is like terrible. But once you do this, right, once you do this, you're at 2. So this, no longer we have this. Now we have 2 times 32, because we've got 2 of these 32 by 32 matrices sitting here, right? So you see your time complexity is already being reduced, plus something to like fix up the, we call this the butterfly matrix. The reason why we're not computing the time complexity for the permutation matrix, and if you've watched my videos on the DES hardware implementation, even the RSA hardware implementation, you'll see that a permutation matrix at the hardware level is instantaneous, right? It's like right away, like there's no time complexity there at all, right? So it's negligible. You don't even consider it. So really and truly, we're just looking at what is going on here exactly. And the main computation to worry about would be these diagonal matrices here, okay? And so the diagonal matrices in this case would be just the W's. So remember we defined the W's, it would just be like this. It would be like W to the 0 all the way to W to the n minus 1, since we're counting from 0. So this is like your W's. So you have W here and then you have negative W sitting at the bottom there. And it's a diagonal matrix as well, so you should already know that it's like pretty sparse already, right? So you can say like about 32 computations for the fixer-upper. Okay, and so that's the Cooley-Turkey decomposition. So what do you do from here, though? Now, from here, there's a recursive step that happens. right? And so what you do is you can split again, and you should see this now, like, because w to the 64 was related to w to the 32, and then you should know then that, okay, well then we can just say, well, w to the 16th is related to w to the 32, right? And so you can decompose this guy into f16s, right? You can decompose this into f16s. And then what you do is you take this even data path, right? This x transpose here, right, and this guy over here, and you can split this now into even evens and even odds. Like, you see what's happening there? And then you split that guy, right, into even odds, and you just keep splitting all the way until you get to W2. And then all the while, your new permutation matrices are operating on these fragmented portions. And then obviously you have your butterfly matrix here that's like fixing everything up. And then obviously, like, you can see this algorithm, but you do need a numerical example. So I would like encourage you to, do a numerical example and see this working for you. But this is used, oh my god, this is everywhere, right? And you can kind of see what's going on here. Like, why is the complexity like n log n, right? It's a binary search tree, really. It's a tree. It's a tree because, like, it's splitting. Like, you see this like splitting pattern that just keeps happening all the time. This is n log n complexity, right? Okay, so should I explain like what this? I can't help myself but like always try to tie in information from everywhere because it really does help you, right? So what is the logarithm exactly? Like, I don't even remember myself, to be honest. Like, these are things I don't memorize, but okay, there is something here, like, so the information theory, some basic information theory, is how I would always try to remember logarithms. And so, how many bits? This is the question, like, you need to ask yourself. How many bits do you need? Oops, to represent x possible states? Like, this is the question you need to be asking yourself. And so, if I had 8 possible states, right? How many bits do I need to represent that? We need 3 bits, right? Do you see that? So if we had 2 to the 3rd, this would give us 8. And so this is like the logarithm question then that you're asking yourself, right? So if we had log base 2, right? Right, this is the question we're asking ourselves. How many bits do we need to represent x possible states? So what is the exponent that we need, right? So we would need 3 bits, and you can see that, like, for instance, if I had 3 bits, let me just do this quickly. We said 0, 0, 0, that's 1 bit, right? That's one possible state. 0, 0, 1, that's another possible state. 0, 1, 0, that's like another. Can you see, like, we're just counting upwards, by the way? 0, 1, 1, this would be, like, whoops, wait, 0, yeah. So 1, 2, 3, 4, this would be 5 possible states, this would be 6, right? And this would be 7. What would 7 be? 7 would be 4 and what? 4 and 2, 6 and 1, 7. So something is obviously wrong here already. So is this 5? No, this is not 5. Oh god. Okay. I don't like the way in which I approach this problem, so I'm just going to come back. 0, 0, 0. This is 0, obviously. 0, 0, 1, this is 1, because I kind of confused myself with the numbering there. 0, 1, 0, this is 2, right? 0, 1, 1, this is 3. 1, 0, 0, yeah, this is 4. 1, 0, 1, this is 5. 0, 1, 1, this is this 6? No, this is not 6. 1, 0, 1, 1, 0, this is 6, right? Yeah, 2 and 4, 6, and then 7. Yeah, 1, 1, 1, this is 7. So can you see then that we've taken like all combinations here, and like we've got like 0 to 7, so this is just 8 total possible combinations that we can have. And so this is really what the essence of logarithms are, right? And then this can be written as like a binary search tree, right? Because so you need like 8. So okay, let's see. 1, 2, and then here, and then here, and then this splits again. 1, 2, 1, 2, 1, 2, 1, 2, right? And so if you were looking for something inside of this tree, right, like you can see then that by picking a direction, right, like if I can only go left or right, obviously, right? I can only go left or right. And so by picking a direction, I've effectively removed half of this tree, which is exactly what was going on here. Right? By picking a direction, I've effectively removed half of the tree. And then by picking a direction again, you remove half of that subtree, right? So here if I said, okay, I'm going right, then this entire portion of the tree is irrelevant. So I'm here now. And here if I said I'm going left, then this portion of the tree is irrelevant. And then, okay, now I'm saying, okay, I'm going to go right or left. And so then you finally end up with your answer. And so it's taking you like 1, 2, 3, literally like 4 steps, right? 4 steps to get here, like 1, 2, 3. Well, in this case, 3 steps to get here, right? And so how many elements are in this tree, though? 1, 2, 3, 4, 5, 6, 7, 8, right? There are a lot of elements inside of this tree, actually. So, like, I hope you see, like, what's going on here. I hope that's clear to you. Like, we've got 8 possible values there that we can pick at on the root nodes, right? 2, 4, 6, 8, right? These are like the states, right? All the possible states that we can have. Like, do you see that? And we need like 3 levels to get there, right? As opposed to having to traverse like every single value to see, oh, come down all the way here, come down all the way here, come down all, right? Like, do you see that? I hope you kind of like, maybe you don't see it exactly, but you get an inkling of what or how this data structure is connected to exponentials and logarithms and that kind of thing, and why the Fourier transform then is like a logarithmic time complexity algorithm. Okay, so that should be it for complex matrices. I don't think complex matrices comes back into this course. And so, okay, yeah, I think I can end it there. What is there left to cover from 1806? I think there's a next chapter on that really talks about symmetric matrices. I think this X transpose AX situation as being a test for a positive definite matrix, right? And there's a definition of a positive definite matrix. And then there's this notion of principal axis theorem, which is very, very important in, for instance, oh god, it's got so many applications, particularly in robotics as well. So, okay, after this one, I think there's another lecture a little bit more on symmetric matrices. Then there's the singular value decomposition, which is the most important factorization of a matrix. There's linear transformations. I think this one is lecture 31. I don't quite recall. Okay, normally you see linear transformations like at the beginning of the course, right? But okay, he like introduces it at the end, which is also quite nice. And then from linear transformations, you've got something else. What is it? Oh, change of basis. There's change of basis. There's also an example in image compression, which is really, really nice to see. And then I think the last lecture, I think it was a quiz. Yes. Okay, you don't have to concern yourself with the quiz. And then the last one was it pseudo inverse, left inverse, right inverse, and pseudo inverse? Yeah. So the course is basically done from here. Like, you've got, like, once you do, the most important thing to do is SVD. Like, everything else is like so simple. Like the hardest stuff you've already, like, if you made it this far, it's just like extending your knowledge a little bit more from here on out. But you've already covered maybe 90% of what the course has to offer at this point. I mean, there's nothing like difficult. You've seen then, you have all of the elementary things that you need to understand these higher concepts, and so they become like quite simple, really. And then from here, you can take 18065 or something like this. Really, really good course, by the way. Here is where you get into some serious applications, right? And then there are obviously like many directions you can go from here. You can go learn machine learning. Like, everything you've learned here will come back in machine learning in ways that you do not quite expect, but you understand so fundamentally, right? Because you've seen these things so well. Normally they just teach you like, oh, like, learn this formula, learn this, learn that. No. Here you just see everything. And it makes sense, and so you can actually solve problems. This is the important thing, right? If you just learn a formula and you don't understand what the formula is or what the formula is doing, you cannot solve a novel problem, right? You won't be able to do that. If you understand genuinely what you're trying to do, right? If you're given a data set, right, you know what you can do with the data set. You can start playing around with the data set. Okay, so I think I've ranted enough. So I'll do one more video. Oh my god, I forgot I left out something on there's like 3 chapters on determinants as well that I didn't do. So I think maybe I'll cover determinants with the last, because I don't want this lecture series to go on too long. We'll just do one more sometime on the determinants. There are, I think, 11 axioms that you need to do. I'm just trying to jog my memory here. There's the 11 axioms, and then you sort of prove them, I think, and you put them to use, obviously. And the main point is determinants are a great way to see volume. That's the key takeaway. And so you do those 3 lectures very quickly. I should probably really knock that up 10 minutes or something, 10, 15 minutes hopefully. And then we'll do singular value decomposition and linear transformations, and maybe the change of basis image compression, and we can probably call it from there. So yeah, we'll see how quickly we can power through these. Maybe, let's say maybe like about 8 lectures or something here. And that should be the end of like linear algebra, MIT 1806, like really, really good course, by the way. Like go take, if you don't understand anything I just said, to go take Gilbert Strang's stuff. This is more so for me, like I can come watch these back at any time in the future and like just recap. Like I have my notes, which are pretty good, but I feel as though like watching a video while you're working or something is obviously a bit more feasible. And yeah, because you tend to forget these like little things, but then just looking back, you can very, very quickly pick them up, right? So, and that's the value in trying to teach others as well. Feynman technique is really, really good because it sort of helps you iron out like some little kinks you might have yourself. Okay, and so I'm not sure where I'm gonna go from linear algebra. Maybe we just continue doing more linear algebra, like go on to some more advanced stuff. I really want to do some hardware implementations though. Like it would be pretty nice to do like a hardware implementation of the fast Fourier transform. And so maybe that would be like a good way to get a numerical example or any numerical example in. And you'll see like how this is used, for instance, right, in compression and things like that. Okay, so like otherwise, like if you have like a really, really large audio file to send over or something, right? So instead of having to send that entire thing, right, you can, and it scales logarithmically, right? So instead of your graph looking like this, oh god, right, your graph is gonna look much better. It's gonna scale much better. But okay, let's say end of notes. Let's put this E. We'll say EOL, end of